Recording. So, hello everyone. Welcome to the very last lecture of Math 1510, Deep Learning Theory and Data Science. I decided to skip the continuation of the lecture that I started talking at the end of the previous lecture and talk today about the topic that we haven't discussed at all during the course, which is basically a different perspective on deep learning. Um, that's a very important lesson. Yeah, putting prints. If there's one thing, if this is the only thing this course has taught you, I think this has been worth the course. Um, Right. So here's the main idea. So I'm going to focus on this paper that I wrote with collaborators from the Technion in Israel. Okay, so here's the main idea. Here's the main idea. Imagine that you take a natural image, for example, an image of a digit 3, and imagine that this image has a generative model that creates this image. So the generative model starts with a certain vector, which here I'm denoting by alpha 3. And this is some vector that maybe encodes, some high-level features or whatever about the image. And then you take this vector, you multiply it by some matrix, and you get another vector or another tensor, I guess. And then this is a different representation of the data. And then you take this tensor and you multiply it somehow by another linear operator, and you get a different representation, which is called alpha 1. And then you take this different representation and you multiply it yet another time with a linear operator, and you get an image. So we call this the multi-layered convolutional sparse coding model for reasons that will become clear soon. So what's important to understand is that this is essentially playing the role of God. You're saying, I believe that natural images are created this way. This is a belief. Okay. Why would one believe such a thing? Perhaps it will become clear soon. Perhaps it won't. It requires a bit of a background knowledge why such a model would make sense. But this represents a belief of how data is born into this world. This is different than a teacher-student model. That's a beautiful question by Neil. It is different. I will explain soon why it's different than a teacher-student model, or maybe I will explain now. In a teacher-student model, actually I'll explain it soon, not now. Okay, so this represents my belief about natural data. Now, more specifically, I believe that each one of these representations has to be sparse in some sense, which means that a lot of the entries in this vector are supposed to be 0, and only a few of them are non-zero. And you can see how the non-zero here are marked with a blue color, right? Now, mathematically, here's how you write this. So here you can see an image, which is a vectorized image X. And I believe this image can be decomposed as a multiplication of a matrix V1 and a vector alpha 1. And this vector is sparse, which means that it has a few non-zeros here. Now, such a belief has a name in signal processing, and it's related to the notion of sparse coding. It Has anyone heard about the idea of sparse coding in their previous lives? Have not. Okay. So this is, if you wanted to, it is like compressed sensing. Yes, yes, very much like compressed sensing. The difference between this and compressed sensing is that do you know what's the difference, Neil? Maybe I should do individual trivia. No? For 5 points of the final grade of this course, Neil. Now it's your individual exam. So the difference between this and compressed sensing is that in compressed sensing, this matrix is random, like random ID Gaussian entries in it. That's the difference between this and compressed sensing. And so notice that this matrix D1 has a special structure where there is a bunch of zeros here and here, and there's certain columns. Compressed sensing is random, and this is not random. Like sparse coding is usually not about random matrices. Compressed sensing is about random matrices. We will get to the question of Justin. The answer is yes, yes, yes. Experts are sitting in the crowd in compressed sensing, it seems. Humble experts who don't reveal themselves immediately. So basically, notice that this matrix D1 has columns which are shifted in different locations, right? Do you see, for example, here you can see there's 2 columns which have compact support, and it's shifted in a bunch of different locations. The way to think about it is think about each column as encoding some type of a local filter of some sort, derivative, wavelet, Haar, I don't know which filters you love or hate. Think about your favorite. Oh, I know a simple filter. Let's just do something like this, right? So what is this filter encoding? This is just a derivative, right? Think of it as some filter, local filter that's moving in all the different positions. So that's a structure that we're imposing on the matrix, okay? Now, we then take this matrix, this vector alpha 1, and we try to represent it as a multiplication of another matrix D2 and another vector alpha 2. So I remind you, alpha 1 is sparse, and we believe that alpha 2 is also sparse, okay? And so the
sorry, I don't know if you explained it already, but what do you mean by sparse?
Oh, sparse means that there is only a few non-zeros which are non-zero. So for example, a vector that's 0, 0, 0, 5, 0, 0, 1 is too sparse. Yes, that is correct, Johan. The white parts are all zeros. 0, 0. Okay. So this is the belief I have about life encoded in equations. Now, and there's different ways to represent this. So there's the way through equations, there's a way through this image, and there's a third way to think about it, which is the deep learning caricature way. People in deep learning don't like equations, they like caricatures more, right? So here's a caricature. I feel like I'm not pronouncing this word correctly. Caricature. Is that even a word? Caricature? It is, right?
Do you mean caricature?
That's what I meant, yeah. Okay, I don't know how to pronounce it as you did. Caricature, is that how you say? Okay. So every time I need to say this word from now on, Gina, please say it instead of it's just, I'll wait for a second, you say it, I continue my sentence. So another way to explain the belief I have about natural data is through this
caricature.
Thank you. So here you can see alpha 2. So here I'm just reshaping alpha 2 into filters by height by width. So it's basically a 3D tensor, right? And you can see that there's only a few of these red boxes which represent entries in the tensor which are sparse. Okay, so this would be a sparse tensor. And then you take this sparse tensor and you apply some linear operation to it, and you get another tensor which is called alpha 1, which is another sparse tensor. And then you apply another linear operation and you get, let's say, an image X. Let's say this image was of a digit 6. Okay. Now, what would be, for example, the operator D1? So the operator D1 is an operator that, I remind you, looks like a matrix that's shifting filters in a bunch of different places, right? And so you can think of its columns as containing filters like those shown here. So these are filters which are essentially building blocks, and these non-zero entries are encoding the locations of these building blocks and also the magnitude by which you multiply each one of these filters. So we've seen 3 ways to represent the belief about natural data. Does anyone have any questions about this? Any questions about our beliefs? No questions. Okay, so here's another way to write this compactly. The signal X, this is the 4th way to write it. The signal X is a multiplication of a matrix D1 times a vector alpha 1. And this thing is just a norm that measures how sparse you are. So I'll explain it in a second a bit more. Alpha 1 is equal to D2. So notice that here we have alpha 1, and here we have alpha 1. Here we have alpha 2, here we have alpha 2, and so forth. It's kind of like a recursive definition of some sort. And all of these alpha 1, alpha 2 have to be sparse. Now, what is this definition of alpha 0 infinity? It's defined formally as the maximal number of non-zeros that appear in a single neighborhood here. So you take a neighborhood here of some specific size that I will not explain what it is. So you take a neighborhood here, like a 3-dimensional tensor, and you count how many non-zeros are there. So let's say in this case, there's 3. Then you do this for all the possible neighborhoods and you pick the maximal, what is the maximal number. So for example, in this case, let's say it's 3 or 4, right? And the belief is that all of these tensors are sparse, but not only sparse, they are locally sparse. Okay. So I'm kind of building the assumptions and then I'll show the result. Okay. Now, in reality, it's very common for you to assume that your observed signal or image is only epsilon close to your, let's say, to your model. How are the KLs chosen? Yeah, that's a non-trivial question. I will not explain how they're chosen. That's a good question, though. That is a good question. That is a good question. I will not explain that. Some of the equations show how they should be chosen, but I will not go into it. So notice that here we have the image and here we have an image in the model, and we can allow a small perturbation. So essentially you can think of this as, there's some type of a, there's a family of all the signals in the model which satisfy our assumptions, and then we're willing to go epsilon away from that model, right? Now this epsilon can be, for example, due to an perturbation that's natural, like if your data, your images are contaminated by noise, or it could be due to adversarial perturbations that we've spoken about at some point in the course. Okay, so then comes the following main idea. If I give you a signal X, an image X, right? And this image satisfies, let's say, these equations. So if I give you X, how can you find, or how can you estimate, given X, the vector alpha 1? If you had to estimate it in a crude manner. Does anyone know?
Yeah, I was going to say something with the inverse. But...
Yeah, so the issue with the inverse is that the matrices that we're using here are usually overcomplete. So that means that the matrix is wide, so it's not invertible. And that's essentially the reason why we're assuming once you have matrices which are overcomplete, it implies that you cannot represent your signal in a unique manner, right? Using columns from the matrix. So what you do is you need to impose an extra assumption about the representation, which in our case is the sparsity. So essentially, if you didn't have the sparsity, then there would be no single representation that would represent your signal over this matrix. So Justin says OMP, that is correct, Justin, but I will not go into that direction. I'm not going into that direction. So one way you could do it is, this might look strange for people who haven't seen this before, but a very standard way to do this that has been around since the 90s is you take your signal X, you multiply it by D transpose, and as a result, you get an inner product of X with each column in the matrix D. And then you apply some type of an operation, which is called soft thresholding. And what the operation does is it looks like a function, like this function. So here's the input, here's the output. Essentially what this operation does is if your D transpose X at a center, at a particular entry is very small, then it's just going to be shrunk to 0. Whereas if it is large, it will just be shrunk by a little bit. So what is this operation S lambda? Let's put here lambda and minus lambda. What is this operation S lambda doing? It's just shrinking entries to 0 if they're small, right? Now, why are we using this particular operation to estimate alpha 1? That will become clear very soon, okay? And this operation is called thresholding. Why is it called thresholding? Because we are thresholding, right? What are we thresholding? We're thresholding the entries in D transpose X. Does anyone have any questions? Any questions? Any questions? No questions. Okay. Now, okay. So here's what I just said. So we take the signal X, we multiply it by this matrix D1 transpose, and we calculate an inner product between each column in D1, right, and X. And then we just apply this operation. And this operation is just going to shrink all the entries that are small to 0. And that gives us alpha 1 hat. Now imagine we take alpha 1 hat and now we try to estimate alpha 2 hat. How could you do that? Just by the same operation, right? So you can just do the same operation. So you multiply it by D2 transpose, apply this soft thresholding operation, and then you get alpha 2 hat. Okay. Now, it turns out that this operation is an operation that's highly related to, does anyone have a suggestion? What does this remind you of, if anything? A ReLU is a correct answer. Now, what is the relation between this operation and a ReLU? A ReLU is just what happens if you don't have this negative thing here, right? So one way to formalize the relationship between a ReLU and a soft thresholding is that soft thresholding is essentially projecting a signal onto the convex ball of an L1 norm, whereas a ReLU is projecting a signal to the convex ball of an L1 norm intersected with the positive orthons. So basically the two are highly, highly related. I can perhaps, the definition would require the knowledge of what is a projection. What? Right, so this is a ReLU with a bias. So if you do ReLU of X plus some bias, so the bias would control the place where you're cutting. So maybe I can say it in simpler words that soft thresholding is assuming that you want to shrink all the entries which are small to 0, right? But ReLU is making an extra assumption that your vector is non-negative. And that's why everything that's negative goes up, okay? Now, at this point, what we have obtained is in fact just a convolutional neural network. Why? Because we take a signal X, which is an image of something, then we multiply by D1 transpose, and Justin already mentioned that D1 transpose is basically applying a convolutional matrix, because you just convolve with one of these, filter in all positions, right? And the second filter in all positions. Then you apply a ReLU, and then you repeat the same process. So you apply convolution, ReLU, and so forth. So what this means is that the model that I described in the beginning was a generative model that if you try to estimate the alphas in that generative model, you get the standard convolutional neural network that everyone's using. Does that make sense? Does anyone have questions? No questions.
I have a question.
Okay.
Like, in this case, the thing that you're trying to adjust and change is like the alpha I, right? Because you're trying to find but in the neural network, you're changing the D instead of the alpha.
That is very correct, yes.
What's the subtlety?
Yeah, that's very correct. So basically, this is assuming that you are given the Ds. The question is, how do you interpret what the network is doing? And you can think of what the network is doing as doing inference under this generative model. That's the point. You are correct about what you said. Okay, now let me skip this. So here's a simple question you might ask yourself. Imagine that you have data X that comes from the generative model that we believe in, generative model, right? And imagine that you take this X and you feed it to a network, a convolutional neural network. So one question you might ask yourself is, are these estimated alpha heads going to be close to the original alphas that created the signal? Why is that question of interest? because, for example, you might think that the alpha 2 contains in its representations, let's say, the class of the image, right? And if you're able to recover through alpha 2 hat, the original alpha 2, you would be able to classify your data correctly. So the belief is that the deepest representation here, let's say, contains class information. And if you're able to recover that deepest representation faithfully, it would mean that your classification procedure would succeed. So that's why this question is of interest. And it turns out that you can actually prove under certain conditions that a neural network will be able to recover the representations up to some perturbation. I won't go into the details because too much time it would take. But essentially what this says is that, let's remove all of this. If your representations are sparse enough, then essentially the forward pass of a network, a convolutional neural network, will find the correct non-zero places, which are called supports, and will find an alpha hat which is close to the original alpha. And so that shows that the network is essentially stable. It manages to recover the underlying representations. Now, from this theorem, you can actually see what is important for the recovery. So Justin seems to be an expert on sparsity, compressed sensing, and everything in between. And the answer is yes. So you can see that the bound on the sparsity of the representation depends on this quantity mu dl. The quantity mu dl is called the mutual coherence of the matrix, as Justin says, and it measures how close is this matrix to being orthogonal. If a matrix, for example, has two columns which are extremely similar, then the matrix is very far from being orthogonal. Can anyone tell me what is an example of a close to orthogonal matrix that we've seen in the course? What matrix have we seen in the course that would be as close to orthogonal as possible, but not very orthogonal? Trivia time. No, what? No, 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 no. Hint, it appears on the website of the course. That's a big hint. Yeah, the ETF, Jim Shaw comes to the rescue. That is correct. So the ETF, if you remember, how did the ETF look like? It was a matrix that had vectors that looked like this, right? And so this matrix is as close as possible to being orthogonal under the dimension restrictions, right? If you have three vectors in two-dimensional space, you cannot force them to be orthogonal, but you can spread them to have equal lengths. Okay. Okay, so I'll skip this as well because of the lack of time. So based on this, yes, they do have a convolutional structure, but it also holds for non-convolutional structures as well. You don't need to have a convolutional structure. By the way, Justin, since you seem like an expert on the topic, maybe I could answer your question from earlier. Earlier, Justin asked, are we going to make RIP assumptions, restricted isometry property assumptions? The answer to that is that if you train deep networks, then they're no longer random. So you cannot calculate the RIP constant of a trained network because it's basically impossible. So that's why we're not utilizing an RIP assumption, among other things that I could discuss at the end of the lecture. So I'll skip this part, but I want to go into, I think, what's more interesting, which is what is the implication of this theoretical result that I just showed you about the stability of a network? So the theoretical result is essentially making predictions about what is important in a deep network for the deep network to be stable, for it to succeed in achieving its goals. So one thing that seems important is for the weights to be incoherent, which means that the weights shouldn't be too close to being to pointing in the same direction. They should be as close to being orthogonal as possible. The second thing that the theoretical result shows is that the features should be somehow sparse. And if you're using convolutional layers, they should be also locally sparse. Locally sparse means that you cannot concentrate all of your non-zero entries in a single location, in a single neighborhood. And the third thing that you can see from the theoretical result is that the success of a deep network depends on the variance of the non-zero entries in the representation. So if the non-zero entries in the representation were of completely different magnitudes, then a deep network would fail. So you want ideally the magnitudes of the representations to be of similar magnitudes. And the reason is very simple. Imagine if you have, if you're using this operation or a ReLU operation, doesn't matter. Since you're cutting at a single threshold, which is the bias, ideally you want all your large entries to be of a magnitude greater than something. And so if you have vastly different magnitudes, it would basically make it very hard for this simple thresholding algorithm to work. I will not define the neighborhoods, unfortunately, Amireza. I can define it, it's hard to motivate it given the limited time we have. But essentially, then if you have a convolutional layer with filters of size, let's say 3 by 3, then the neighborhood that you should look at is of size 5 by 5. So basically it's 2k minus 1, where by 2k minus 1, where k is the size of the filter. But I don't have time to explain why that is the correct number to be looking at. Okay, so one interesting thing, yeah, so that's one of the predictions of this work, that using thresholding is probably a bad idea, and you want to use something like iterative self-thresholding. And essentially, if you use iterative self-thresholding and you write down the equations, you see it's very similar to what a ResNet architecture does. So our interpretation of a ResNet architecture is an iterative self-thresholding algorithm that was unfolded. If those words make any sense to you, Justin. If you're interested in this particular topic, look for something called LISTA. There is a work called LISTA by LeCun and co-authors, LISTA. I think you would find it very, very interesting. So one prediction that we have from the work is that if you are under a perturbation which is adversarial, so if someone's attacking you with an adversarial perturbation, then the distance between the estimated alphas, which are denoted by alpha hat, and the true alphas is actually going to grow exponentially with depth. So essentially, in the first layer, the distance might be this big, then it will be significantly larger, 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 and so on. And you can characterize why is that increasing exponentially fast. Another prediction that we have in the work is that the first layer of a network should be the type of filters that you would observe when doing something like dictionary learning or sparse coding in the context of neuroscience. So in neuroscience, people found that if you do if you train the weight matrices and you impose sparsity on the representations, you should find this type of edge detector filters that look like this, or like that, or like this. Actually, I shouldn't even draw when I have a picture. And it was observed in deep networks that similar filters emerge in the first layer of a network, right? So this is in AlexNet, and this is an experiment that was done in 1996 by Olshausen and Phil, who are some of the greatest researchers who worked on this topic. So you can see how the filters here look like edge detectors, right? And these filters were obtained by training a weight matrix to represent data with sparse representations. So essentially sparsity leads to this. And in a network, you see this, which is somewhat close. So that's evidence that some type of sparsity is being employed in the network without you even noticing. Another prediction that we have based on this theoretical result is that the sparsity of the features should increase with depth. And that's something that has been observed by people. And yet another property that we predicted was that the last layer features should have some type of a block sparse structure, where essentially the non-zero entries are organized according to the classes. So if you look at the last layer representation, you would have like representation. The first entries would encode cat, the second entries would encode dog, and so on. And this is called block sparsity in the signal processing literature. And what happened over the years since we published this is it seems like people are finding more and more evidence that something about this whole story is in fact correct. So for example, here you can see a measure of sparsity of the representations as function of depth for networks such as VGG, AlexNet, and different types of VGGs. And you can see how the VGGs and the AlexNets are essentially becoming closer and closer to being sparse as function of depth. So if you look, for example, at this VGG, very deep, 16, you can see how initially you have something like 70% sparsity, but then it climbs all the way to 90% sparsity. So for whatever reason, the representations are becoming sparser and sparser with depth. Okay, so there's a video, I don't think I can, maybe we can see it. Wow, YouTube.
Wave Hybrid was designed for people
Let us watch
who are having more trouble getting a comfortable night's sleep.
Does anyone have Casper?
In their body. So we designed the Wave Hybrid.
Right.
Recent advances.
First, let us like this person and let us subscribe to this person.
They can recognize school buses and zebras.
What was the other thing I was recommending except like and subscribe? Right. So the bell.
But we don't know so much about how they're actually computing their final answers.
Okay.
We developed this interactive deep
let me mute this person.
To shine light into these
how do you mute this person?
Showing what happens inside of neural nets.
Oh, right. So back to the point. The point is that this person is visualizing the representations inside a network. I am watching a YouTube inside the YouTube. That is correct. So what this person is doing is he's showing you the representations deep inside a network. So this is layer conv1. And if you skip through the video, this is, for example, layer conv3, right? Can you see anything here that looks relevant to our topic of discussion today? Does anything strike you interesting about this visualization? It is sparse. Thank you, Nia. Yeah, so you can see that most of the representations are just black, dark, and there's only a few non-zeros, which are the light spots, right? I guess here it's, yeah, so you can see, for example, again, mostly dark. So this seems like an empirical some type of empirical evidence that the representations are in fact sparse. Another thing that people have done, so this researcher by the name of Shang in 2015 actually calculated the inner products of the different filters in a network. So that's essentially equivalent to calculating this mu-d, which is a measure of how close are the filters to being orthogonal. And what she found was that on average, the filters are pretty close to having a very small inner product. So these numbers are the inner product of two filters in the network. And you can see that the inner product is pretty small. So, you know, by Cauchy-Schwarz, if you take a filter, let's say Fi and a filter Fj, and you look at their absolute value divided by the norm of Fi times the norm of Fj, right? And let's say you average over I and j, which are not equal, right? That's what's written here. Then this quantity would be between 1 and 0. The closer you are to 0, the closer are all filters to being orthogonal. And what this person was showing is that it seems like for whatever reason, the filters in a network are in fact close in some sense to being orthogonal. Does that make sense? Does make sense. Okay. Right. So another evidence for why sparsity is this paper. So if you read this paper, what they are suggesting is to regularize the weights of a network to become closer to being orthogonal. So essentially, they're minimizing the loss of a network that depends on some parameters theta, and they add to this loss some type of regularization like WW transpose or W transpose W minus identity, which essentially promotes the weights to being orthogonal. And they found that this leads to better adversarial robustness, better performance, etc., etc. So our theoretical result is saying that the closer you're to orthogonality, the better you will perform. And these people seem to be corroborating this statement. And of course, perhaps the most relevant example to this course is that we've seen that the last layer of a network undergoes neural collapse. And in the process of neural collapse, your classifiers tend to this simplex ETF structure, as Jim Shaw has reminded us. And this simplex ETF structure is literally the optimal configuration you might have given the configuration, given the dimensions, basically. So this is yet another evidence for why there seems to be sparsity and orthogonality in the network. So there's more and more papers. I didn't do an exhaustive search, but here's another example. What are they doing here? Yeah, I won't go into it, but basically more and more examples contain the words robustness, sparsity in their title. Okay, so that's the summary. Essentially, the main idea is that by imposing the generative model of the multi-layered convolutional sparse coding, you get a theoretical result that sheds light on under which conditions are deep networks going to succeed in recovering the representations and under which conditions they will not. And I think this is very interesting because it connects deep learning to basically 30 years of work in signal processing of studying this type of generative models. So this is the end. Thank you very much. And I remain for questions. Thank you very much. Thank you very much. Thank you, Luke, for the kind words.
Can I ask a question?
Yes. Yes.
So the fact that you have a ReLU showing up or a soft threshold here comes from like a basis pursuit problem, right? L2 squared L2 plus L1.
Yeah, so basically soft thresholding is a crude approximation for the solution of a basis pursuit problem.
Yeah. So is there anything fruitful that you can do by taking, like, can you explain other nonlinearities via different regularizers in that sort of problem?
Probably, but we didn't try to do that. But probably
Okay.
you can, yeah.
Yeah.
Essentially, since you bring up the basis pursuit, if you had a problem that would be something like this, and you add the alpha greater or equal than 0, that would result in the ReLU.
Right. But if you picked something crazy for the regularizer, you could potentially get different.
Yeah.
And yeah, I was wondering if anyone's tried that and gotten like new nonlinearities.
No, but there was something quite funny that happened. I don't think the people are aware, but basically, I think it was researchers from Google who spent a lot of money trying to optimize nonlinearities. And then what they found was that the optimal nonlinearity looks something like a more curvy thresholding thing. So it's like everything is more curvy. And that's the kind of nonlinearities that you see when you do an MMSE approximation of a sparse vector.
Interesting. I'd be curious to find that out, how they optimized for that.
Yeah, I'm not sure about that.
Yeah. That's neat.
Mm-hmm.
So I had a question. I was wondering about, so you're talking about how this is sort of equivalent to unfolding some other algorithm, right? That this is what the neural net is doing. Is that kind of true?
Yeah, but the thing is that so instead of this thing and instead of this thing, you could unfold an algorithm. The whole neural network, from my interpretation, is a series of unfolded algorithms.
Yeah, I see.
But the difference
go ahead.
between unfolded algorithms and a neural network is that in an unfolded algorithm, usually you would tie the weights to be equal. Like if you think about, the solution of some iterative soft thresholding, the dictionary is fixed throughout the iterations, whereas in a network, you don't fix the dictionaries to be equal.
Yeah. So I was wondering, like, if D is dense, is the right thing to do some sort of unfolding of like a AMP type?
Yeah, so people have done that. I think in Duke, they tried using AMP type of thing. I think AMP is more of an algorithm that you use if you have random matrices, right?
Yeah, I think that's true. I think the analysis has been done with random matrices, right? But I think that there's a lot potentially to exploit structure, additional structure and sparsity that people are doing, looking at how to. I think it's hard to do the analysis basically when you don't have a random matrix. But if you all the analysis, all the theoretical guarantees are typically done with that. But I think the algorithm works.
Are you aware of people actually using AMP in a setting of a real life application?
Yeah, we use it like all the time in signal processing for like communication systems.
And does it actually perform better than like Vista or something?
Yeah, it's very good. There's variants of it that we use, like this multiple measurement vector. So sometimes we have systems where we have many antennas all measuring the same thing, just with different noise samples. And as long as the problem isn't so huge, AMP is often our best solution. It's compromising complexity, making compromise between complexity and performance.
Interesting. Yeah.
So yeah, I've seen it a lot actually.
Yes, Emerson?
Can you hear me?
I can.
Okay, I have two questions. The first one is I want to know what motivated you to assume these sparse representations for these images. I mean, did your motivation come from neuroscience and this stuff, or from the background of signal processing?
Background from signal processing. I spent my whole PhD doing signal processing, so that's kind of the influence, I would say.
Okay, I see. And the second question was about the presentations that we're going to have on Monday. I wanted to know if there is any order, predefined order that we're going to present our projects, or
No.
is it in random?
No, it's probably random. And Gina said that perhaps if we do it over 2 days, like if we had it on Monday and Thursday, then some people would refuse to volunteer. So I'm thinking maybe we would just do 3 hours consecutive on Monday to make it more fair. So other people don't have more time to work on the presentations then, you know.
Yeah, that would be fair. Yeah. Great. Thank you.
It's just that 3 hours is a bit, it's a bit too much. Maybe we'll have a break or something. By the way, regarding your first question, so there was motivation for why doing this. Basically, if you look at the signal processing community, there were a bunch of works that made the assumption that a signal is a multiplication of a matrix times a vector, right? So the sparse coding part is very clear. The reason why you would do the second thing is that there were actually a bunch of works in signal processing that showed that the representations themselves have structure. Like if you just run sparse coding on natural images and look at the representations alpha 1, you would see they have a bunch of structure in them. And so it makes perfect sense to try and capture that structure through a different model.
Okay, I see. But are they locally sparse or just
locally
sparse?
Yeah, locally sparse. The reason for the locality is because we've shown that in a different work that I didn't discuss, that if your matrix is convolutional, you want the dictionary to be, you want the representation to be locally sparse, not globally sparse.
Okay, I see.
Because if an adversary concentrates all the non-zeros in a single neighborhood, it would completely mess up the recovery. I don't know if that's an intuitive statement for you.
Oh, I see. And that's why you defined the local sparse in a range of 2K minus 1 elements. That's the range a channel, if filter can convolve or consider during one iteration of convolution.
Exactly, yeah.
Okay, I see. Okay, thank you.
Hi, Professor, can you hear me?
Of course.
I just have some basic questions. Why do we need the code be sparse? Like when the input is not sparse, what kind of problem will they cause?
I think that's a beautiful question that has no answer.
Okay.
I think that intuitively speaking, you can prove that if you're working with over-complete representations, then the sparser you are, the better your recovery is going to be. So sparsity is essentially a measure of the low dimensionality of the data.
Okay.
And these sparse coding algorithms are essentially projecting your high dimensional signal into a low dimensional subspace. So if your subspace is very low dimensional, then by doing the projection, you're killing a lot of noise.
Oh.
But I want to clarify that you could train a deep network, I think, and perhaps you wouldn't see as much sparsity as you would like. So it's unclear whether it's a necessary condition to be sparse, if it's necessary for you to be sparse in order to perform well. That's kind of a thing that I haven't seen anyone really explain.
Okay. Oh, and another question is like, after we make it sparse, like how do we know the result will be accurate, like compared to the case where we didn't make it sparse, like
I think theoretically you can analyze this and show that the sparser you are, the more likely you are to recover the underlying vector. Empirically, there's been a lot of theoretical work on this model, which is the single layer model, so to speak, that shows that the sparser you are, the more likely you are to recover.
Okay.
For multi-layer, it's a bit more complicated.
Sorry, what do you mean by recover?
For example, that alpha hat is close to the underlying alpha in some norm.
Yeah. Oh, okay.
So just related to that, you mentioned that people have been looking at natural images and trying to justify this model. So is something like using like an autoencoder or something like that, is that how they're doing this? They're saying like we can use some feed forward neural net and show that, oh, actually we can represent this as some sparse vector and we can reconstruct it, or is that
no? It's actually usually done using dictionary learning. So dictionary learning is let's see. Dictionary learning is this algorithm that allows you to take a bunch of images and train the sparse vector and the weights at the same time. Here it is.
Mm-hmm.
So what you can see is that in this optimization problem, you're optimizing both over W and the alphas of the data.
I see.
And what they have observed is that if you solve this problem, then you get these type of filters. And the representations are actually sparse.
I see.
So that's how people motivate it in neuroscience.
That makes sense. Okay.
But there's also other things. For example, people have observed that the representations of natural images have this type of linear trend on a log scale, which seems to indicate that the distribution of the representations follows some type of a Laplace distribution. And Laplace is basically the Bayesian way of saying L1 norm. So there's various ways in which people, explain why natural data is sparse in some basis.
Yeah. That's interesting because I see like a lot of people talking about contextual compression of images. Like if you have some idea, have some model or some idea of what the context of this image is, perhaps we can do some much better compression, right?
Yeah.
And so it's interesting from that perspective as well.
Yeah, so that's very related. Basically, you're saying that if your data is coming from a specific family, then the learning of the parameters will be able to customize the weights to that specific family. That's literally what dictionary learning is doing, and in some sense also what deep learning is doing, right?
Yeah. Interesting. Okay, thank you.